In this video we're going to talk about temperature, what it is and how we can measure it and what unit we use to measure temperature. We usually think about temperature as just meaning how hot or cold something is, but that's not the best definition of temperature, because if you think about what cold and hot actually mean, it's not that simple. So if we look in the dictionary, we can see that cold is the opposite of hot and hot is the opposite of cold. But what are they really? Well, one way to answer that question is to think about how we measure temperature. So we usually use a classic thermometer to measure temperature, which is a hollow tube made of, for example, glass, and then it's filled with liquid. And the thing about liquids is that they expand when you heat them up. So if we put this thermometer inside some ice which has just melted to become water, then we know that it's going to be at 0 degrees Celsius. And then we can keep the thermometer there until we boil the water. And where the water starts boiling, we can call that 100 degrees Celsius. And then we can simply split the scales. We split this into 100 equal divisions, and that's our centigrade scale. So let's think a little bit more about how this thermometer works. So if we have a hot object and we put it next to a cold object, then it's called that they're in thermal contact. And we know that the heat always flows from hot to cold. And the heat is going to continue to flow until the two objects are at the same temperature. So temperature T here. And when they're at the same temperature, there's no heat flowing. And the term that we use in physics for that is thermal equilibrium. Okay, so let's go back to the thermometer that we had. And say that we want to measure the temperature of a glass of water. Then basically what we want is for the thermometer itself to be in thermal equilibrium with the water. Otherwise we're not going to get the temperature of the water itself. So we put the thermometer in a glass of water, and then we have to wait. Because we have to wait for the heat to flow from the water if the water is hotter than the thermometer. And as soon as they're in thermal equilibrium, we can read off the temperature. So let's look at the molecular scale to see what's actually going on when we change the temperature or something. So here we have a container, and I'm going to put some gas molecules into it. And let's let it stabilize for a bit. Okay, so here we have some gas at 300 kelvins. And if we bring out the properties, we can see that the average speed of the gas molecules is about 1,100 meters per second. So let's see what happens if we add or remove some heat. So let's start by adding. So it's a bit hard to tell what's happening just by looking at the molecules, but if we look in this window here, we can now see that the average speed is 1,500 meters per second. So the average speed went up and the temperature went up when I added some heat. So let's do the opposite and remove some heat. So we'll go below 300 kelvins where we started. So let's go down to about 200. Okay, so at 200 kelvins, we see that the average speed is about 900 meters per second. So there's a relationship between how fast the molecules are moving and what the temperature is. But because molecules of different masses would have different speeds at the same temperature, we also have to take the mass of the molecules into account. So we can actually say that temperature is not just a measure of how hot or cold an object is, it's also a measure of the average kinetic energy of the molecules that make up the material. So let's underline that very important part about the average kinetic energies, just so it doesn't get lost in all those other words. So we saw that molecules at low temperatures move more slowly than molecules at high temperatures. So surely that means that if we cool something down enough, there's going to be a point where we can no longer cool it down anymore. And this is the basis of the Kelvin scale. This temperature scale is named after Lord Kelvin, who wrote a paper back in 1848 saying that instead of using the freezing point of water as the 0 degree, we should use the coldest possible temperature, the absolute zero. So let's draw a Kelvin thermometer next to our normal thermometer. And we're going to put 0 at the absolute 0, which is the lowest temperature that we can possibly get to. And if we decide that the size of 1 Kelvin is the same as the size of 1 degree Celsius, then it turns out that our normal 0 degree Celsius the freezing point of water, is going to be at 273 kelvins. And that means that 100 degrees Celsius is at 373 kelvins. So to recap, the size of 1 Kelvin is the same as the size of 1 degree Celsius. So if we have a thermometer that shows both Kelvin and Celsius, then that means that the distance between all the lines is always going to be the same. It's just that the Kelvin scale is shifted by 273 degrees. And this is actually really important because it means that when we're talking about temperature change, we don't have to worry about whether we're talking about Celsius or Kelvins. Whereas when we're talking about absolute temperatures, we do have to worry about it. And we have to convert from the Celsius into Kelvins if we're doing some calculations. So now let's do a couple of examples to finish off. So first of all, if we had 300 kelvins, what would that be in degrees Celsius? Well, all we have to do is to subtract 273 degrees because the scales are just shifted by 273 degrees. So we do 300 minus 273 and we get 27 degrees Celsius. And if we go in the opposite direction, from Celsius to kelvins, we can do 80 degrees Celsius and think about what that would be in Kelvin. Well, since we subtracted 273 before, to get from Kelvin into Celsius, that means that we're going to have to add 273 degrees this time. So we do 80 plus 273, which is 353. So 80 degrees Celsius is the same as 353 kelvins.